Hello, so this video is going to be about differentiating the function, the natural logarithm of sine of x. So that's what we're going to calculate, the derivative of this function here. So you'll probably notice that this is going to be a chain rule example, if you've seen my previous videos, because we've got this sine function inserted into this natural log function. So we're going to need the chain rule. But before we do that, let's just consider the domain of possible x values in which this natural log of sine x is defined. So we know if we just sketch a graph of the function of the natural logarithm, so it looks something like this, crossing through at 1 there, and this is ln of x. So we know that this function is only defined for x values greater than 0. So it must be true that this natural log of sine of x is defined for sine values greater than 0. So this is defined for sine x values greater than 0. So where is the sine function greater than 0? I mean, let's just do a little sketch down here. So sine of x kind of looks like this roughly. So we've got 0 there, we've got pi there, 2 pi there, 3 pi there, and so on and so on. So what we can see then is that when x is between 0 and pi, 2 pi and 3 pi, 4 pi and 5 pi, and so on and so on, the value of sine is bigger than 0. And in order for this function to be defined, we require that this sine function is bigger than 0. So this is bigger than 0 when x is in the open interval. So from essentially the even multiples of pi. So let's just say 2k pi up to the odd multiples of pi. So 2k plus 1 times pi, where k is an integer. So yeah, it can be the same with the negative values as well. Yep, so that's how that's defined. And obviously, yeah, with these negative values, you've got minus pi there, minus 2 pi there. So as long as x is between these range of values here, then we have a defined log of sine of x function. Okay, great. So now let's go ahead and differentiate the function. So yeah, when we differentiate this, we're going to use our chain rule. So natural log of sine of x. So using our chain rule, so just make a note that this is the chain rule. So we're going to differentiate the entire function that we have, but differentiate that with respect to the variable inside the ln function. So with respect to the sine variable, and then multiply that by the derivative of the sine function, but with respect to the variable x. Okay, great. Let me just move my writing up a little bit to make more space. Didn't mean to do that. Let's do that again. Okay, let's move it there. Okay, so we know from previous videos that when we differentiate the natural log function with respect to some variable, we literally just get 1 over such a variable. So this first derivative is going to come out to be 1 over sine of x. So yeah, differentiating log, the natural log of a variable with respect to that variable, you get that variable. So we get 1 over sine x there. And then if we differentiate the sine function, well, we know from one of my early videos that this is going to give us cos of x. And so just by multiplying those two things together, we get cos of x over sine of x. And well, we know that this is just the same as the cotangent function, so cot of x. And so what we can say then, or what we can conclude, is that when we differentiate this natural log of sine of x, we get the cotangent function, but the x values, in order for this to be true, are only work in the cases when x is between even multiples of pi and odd multiples of pi in that open interval, like so. So for example, again, I'll just make a note that k is an integer, can be any integer. So for example, this interval is obviously going to include 0 up to pi. It's going to include, so 2 pi up to 3 pi. It's going to include 3 pi, sorry, not 3 pi, 4 pi up to 5 pi. And also the negative values as well. So it's going to include, so negative 2 pi up to pi. It's going to include, what other values have we got? So yeah, it's going to include negative 4 pi up to negative 3 pi, and so on and so on and so on and so on forever and forever. So yeah, that's the derivative for this video, and yeah, that is how you will define the domain of such a function.